Okay, so you can hear me, right? So I will not play the video. I just can you see the screen? Okay, so I'll let me tell it. So today we'll solve this Gate 2023 question from complex analysis. It is question number 50. It is saying that let D be the unit disk and F is a function from the unit disk to complex plane. The function is given by this, and the two options are given. That F has 3 zeros in the unit disk and F has 1 zero in the this annulus from half to 1. You have to say which options are correct. Okay, so this is the NPTEL reference. So in order to solve this problem, we will use the Roche's theorem. So which counts means which will compare between two functions. If one is, we will take some simple function or homomorphic or analytic function, for which you can easily tell that what are the number of zeros. And using comparing with that function from this one, we can tell about the number of zeros of this function. So this is given by this Roche's theorem. What did it say? Suppose two functions f and g are analytic inside and on a simple closed contour C. And suppose this fz is strictly bigger than mod gz. Mod of fz is strictly bigger than mod gz on the closed contour C. Then you can say that fz and fz plus gz have the same number of zeros. Obviously, this is counting the multiplicity inside that contour. So this is basically saying that if this inequality, strict inequality is satisfied, then you can compare the zeros between f and f plus g. Okay. So let f is given as early. So what we will take? We will take this h equals to this simplified function h. We will compare between h and this f. For h, this is simple looking function, right? You know how many zeros for h. This is a 3-degree polynomial, and in the complex plane, so it must have 3 zeros. And take gz equals to the remaining, because we want h plus g to be the whole f, because we want to compare between h and f. So that's why we have taken h and g to be like this. And we have taken the contour C to be the boundary of the unit disk, mean basically the unit circle. So on the boundary we need that strict inequality. Okay, so check on the boundary what is mod hz. Mod hz basically is 25, right? And what will be the mod gz? So mod gz just use the triangle inequality. So using just triangle inequality we will get the first line. And on the boundary mod z is 1, so put it there. So you will get the next one. And you know that all these functions, all these 1 by 5 factorial, 1 by 7 factorial, all these are less than 1. So this is basically less than 5. So you can easily see that on the boundary, this is satisfied. Mod gz is strictly less than mod hz. So the condition for the Roche's theorem is satisfied. So you can from that you can say that hz and fz has the same number of zeros, counting multiplicity inside this unit circle, right? And what is hz? Hz is this to a minus 25 z cube. So it has 3 zeros inside the unit disk. So therefore f has also 3 zeros inside the unit disk. Mod z equals to 1, right? Mod z strictly less than 1. So therefore the first option is correct. F has 3 zeros. So this is obviously counting multiplicity. So it has 3 zeros inside unit disk. Now I have to check the next one. So this is saying that on the annulus, this annulus from half to 1, how many zeros are there? It is saying 1 0. So in the unit disk, what is the strategy for solving this one? So in the unit disk, we have shown that is a 3 zeros. If we can show that inside the disk of radius half, so there is all the zeros are also there, then in this annulus there will be no zero, right? So we'll show that one. We'll show that now. In the annulus, we have to show that it has 1 0. We'll show that this is not true. So for that reason, we have take this contour to be the now the circle of radius half. And again, we choose the earlier function hz equals to minus 25 z cube, and gz the remaining of from f. What is the remaining function? And now on the circle of radius half, Mod of hz is basically 25 by 8. And what is gz? On that circle of radius half, gz is basically, as I'll use the triangle inequality, and mod z equals to half. Use this one, then you will get the first inequality. And now all these are quantity are less than 1, so you will basically get 5 by 2. So mod gz is less than 5 by 2 on the circle of radius half. So therefore you can compare, right? Now these two. So what is the bigger? So a mod of hz is bigger than mod of gz on the circle of radius half. So therefore we can use the Roche's theorem. So using that Roche's theorem, we can say that hz and fz has the same number of zeros, counting multiplicity inside this mod z equals to half. And what is hz again? This is the minus 25z cube. So you know all the zeros lying inside the, so because all the zeros, what are the zeros? It's only the 0, right? Counting 3, multiplicity here is of 0 is 3. So hz has 3 0 inside this circle of radius half. So therefore fz has also the 3 zeros inside this circle of radius half. So earlier we have get what we have got, that fz has 3 zeros counting multiplicity inside the circle of radius 1, and it has also 3 zeros inside counting multiplicity inside the circle of radius half. So therefore all the zeros, it means there are no zeros in the annulus, right? Because you have taken again the half radius of circle, all 3 zeros are there. Means there is no zero in this annulus, right? So therefore the option number Q, it is false. So therefore first option is correct, P is true and Q is false, right? Okay, any doubt? Any question? Yeah, fine. I will share this. This video you can see in the NPTEL website, or I will also upload in the YouTube. So from there you can see the video. Others, for everyone, is this clear? What I have said about the question? Question number 15. Okay. So we'll next move to the next question then, if this is clear. Okay. So the next question is again from complex analysis. This is question number 27. What it is saying, a holomorphic function is given z by 1 minus z minus mod z square in a neighborhood of 0. It is holomorphic obviously, and it has expanded in terms of power series. So n equals to 0 to infinity a n z to the power n, but the coefficients are real number. You have to find the, so this is a in some neighborhood of 0 in the complex plane, saying that you have to find the coefficients here, the a6 and a5. What is the a6 plus a5 in the power series? right? You know, if you write any holomorphic function in terms of power series, you know how the coefficients are look like, right? It is given by the derivative of that function of certain order, right? So therefore that you can also do, but if you do that, you can, this problem you can do it also other way. So let me do it. So this is the NPTEL reference for the theory. This is, so we'll do it basically the other way. So so this, for that we need a one observation, that what is in the denominator, 1 minus z square. So look at this polynomial. If you solve what are the roots of this polynomial, so it has basically two roots, right? If you solve these two, what are the roots? The roots will look like basically minus 1 plus root 5 by 2 and minus 1 minus root 5 by 2. Is this roots, do you look familiar to you? You know about this polynomial? Anyone know about this polynomial? Or anything about the root minus 1 plus root 5 by 2? What is the speciality of this root? Any connection? Yeah, so this minus 1 plus root 5 by 2 is the golden ratio. So this is connected with the Fibonacci sequence, right? You will basically show that this 1 by 1 minus z square, this is generating function for the Fibonacci sequence. So what is meant by the generating function of some sequence? So this function you can write as in a formal way, not so you have ignored the convergence or anything. Summation of that sequence as a coefficient sine z to the power n, right? So this means that this is the generating function of that sequence. So we'll show that basically this function 1 by 1 minus z square is a generating function for that Fibonacci sequence. So now let's recall what is Fibonacci sequence. So Fibonacci sequence basically sequence where the any term is the basically the addition of the last two terms. First we will use start from 1, b0 is 1, b1 is also 1. And what will be the next term? So add the just previous two terms. 1 plus 1, it's 2. B3 will be the adding of B1 plus B2, so it will be 3, so like that, and so on. So Bn you can, for n greater than 2, you can write as a Bn minus 1 plus n Bn minus 2. This is the general formula for Fibonacci sequence. This is the recurrence relation. So we want to write this function as a formal power series like this, where Bn's are the Fibonacci sequence. Okay, so let me call this power series to be fz. And how you, so you'll just write the n equals to 0, it is b0 is 1 and z to the power n is basically 1, so 1. And if you put n equals to 1, what you will get? Again b1 is 1 and z is basically z, so it is 1 plus z. And now write the remaining as a series from n equals to 2 to infinity, b and z to the power n. Now because this is from n equals to 2 to infinity, now you can use that recurrence relation for the Fibonacci sequence. So how you can write? You can write this, just replace bn by bn minus 1 plus bn minus 2. And now split this series. So what is then become? Then it will become 1 plus z plus summation n equals to 2 to infinity bn minus 1 z to the power n plus summation n equals to 2 to infinity bn minus 2 z to the power n. Now make a change of variable. Just what is change of variable for this discrete? Just put n minus 1 equals to some k, right? Then again I am writing k to be this n, means bn minus 1. I just make it k. Then what will be n? N will be k plus 1, right? So basically this is k plus 1. And sum will be, if you put n equals to n minus 1 equals to k. So when n is 2, k will become 1. So that's why the sum become from n equals to 1 to infinity. So this is a change of variable for discrete series, right? Discrete situation. And again in the next series you will make the change of variable for n minus 2 equals to k. So then this will become the summation from n equals to 0 to infinity bn z to the power n plus 2. Now Okay, so you will take the common, this from Z, take out the common, it will become, from the first series, it will become n equals to sum from n equals to 1 to infinity bn z to the power n. And from the second sum, take out the common z square part. Then it will look like summation n equals to 0 to infinity bn z to the power. So we have started with fz with this summation from n equals to 0 to infinity. So the next last term of the series, it will again become fz. But the middle term, summation n equals, it is from summation n equals to 1 to infinity. So in order to make this sum from n equals to 0 to infinity, we have to subtract the first term, because first term is not here. So that's why I have written in the middle part 1 plus z. Inside bracket we have written this series from n equals to 0 to infinity bn z to the power n. Sorry, this will be bn. And you have subtracted the n equals to 0th term. So n equals to 0, b0 is 1 and z to the power n is basically 1. So that's why I've written this summation series from 0 to infinity minus 1, and the last one as it is. So note, then you can write this is 1 plus z into this become fz minus 1 plus z square time again fz, right? So take the all the z's in one side and z square part one side. So it will become 1 plus, so z and plus z and minus z will cancel out. So it will remain 1 plus z fz plus z square fz. Now, if you solve in terms of f, what you will then get? You will basically get that fz is 1 by 1 minus z square. So we start with this series, you have to start, and we are going to get that f is this holomorphic function. So therefore, it is saying that this function is, you can write in terms of this generating function or power series in a formal way, where b zeros are the Fibonacci sequence, bn's are the. So you have get this, that this is the basically the generating function identity for this function. So therefore now we have to find out the power series for z by 1 minus z square. So just multiply this what you have got by z. Then it will become summation n equals to 0 to infinity bn z to the power n plus 1. And which we want to be, we want to find this is a n z to the power n, and which is, because this is equal to this one. So you have to write again this equality. Right hand side is from the question. And what is the first inequality is basically what we have derived. So if you compare the last two equality, means summation n equals to 0 to infinity bn z to the power n plus 1, and the last one is n equals to 0 to infinity a n z to the power n. From here, what can you conclude? That this is basically the, if you put 0, b0, what is b0? Basically b0 is the coefficient of z, and here a0 is coefficient of z is a1. Coefficient again z square is basically the b1, and coefficient of z square is a2. So if you compare them for n greater than equals to 0, you can see that bn equals to an plus 1, right? So therefore, what will be a6 plus a5? It will be basically simply b5 plus b4, right? And what is b5 and b4? Because these are Fibonacci sequence, you can just compute. We have computed earlier. What is b4 is 5, and b5 is 8. So it is basically the sum of these two. So 8 plus 5 is 30. So therefore, 8 plus a6 plus a5 is 30, right? Okay. Any questions? Is this clear? I think the same problem happened yesterday, means last time. You cannot hear the video also, right? Any doubt from the last class? Then I can also explain that day's class. Yeah, any other questions? Okay, fine. And any doubt from the last class, because it was also same thing happened. Have you seen the last class's video? Any doubt with that? Last time we have solved two questions from measure theory, right? If you have any doubt in understanding something, you can tell me. No doubts? Yeah, means this question you can also solve using what you can do this, just do the partial fraction. Then it will become something simpler. Suppose take the golden ratio, take this sum root alpha, and it will satisfy this identity, right? Alpha square minus alpha plus 1 equals to 0. So it will become something like 1 by z minus alpha minus 1 by z minus beta. And if you know the formula for the nth coefficients a and how it will look like, it is basically derivatives n times by n factorial. If you plug in there, you have to use that this is a golden ratio, means alpha square plus 1 equals to minus 1. If you use that, you can also easily get that. But if you can recognize that this is a genetic function for the basic Fibonacci sequence, you do not need to compute the derivative. You will easily get this because this is basically the just the shift multiply by z with the genetic function for the Fibonacci sequence. What is the question? Mod z minus 1 equals to 2. Then integration over what is Varsi of tangent by tangent? What is this? Varsi, what is this? Integration over C. Okay, okay. Oh, so this is basically integration of tangent by z, and this is the modulus of basically circle centering at 1 of radius 2. Right. So just because this is a at the point 1, what is this tangent by z? Yeah, that's fine. So if you can write down the power series in terms of no, but this is in the circle of radius centered at 1, right? Not centered at 0. Because you have to write down the power series of tangent. Otherwise, what you can do z by z minus 1 plus, no, that will not help. You have to just parameterize. Take the equation of the circle centered at 1 and of radius 2. You have to put it there and you have to integrate. You have to see what it will come. Just you have to take the parameterization of circle of radius 2 centered at 1. Okay, I will check what will be the integration. Means it will come easy or okay, I have to check it. Otherwise, means if you can show that in a neighborhood of 1, the power series, because it will certainly converge. So therefore, if you can integrate, yeah. So for that you need how many? So inside, but it is a circle of. So how many zeros are there? For that you have to check of that. So 0 is certainly something. So if you write down the, you have to write down the power series in terms of z minus 1, right? So how many zeros are there? You have to just calculate. Because certainly it does not have any poles there. So number of zeros of radius. No, I think no, there is no pole. Zero is included there. Yeah, I will check what is the answer. It is minus 4i. Okay. Let me see. There are easier way of solving this or not. One way you have to just parameterize, but I think that will be some difficult if you parameterize it. So you have to use some kind of formula. But it's certainly given that power series centered at 0, then you can integrate, right? And after sometimes it will get holomorphic function, so it will become 0. So you will certainly some number of terms will only contribute. But here you have to write down power series in terms of z minus 1. That's the only thing, only difference. Any other question where you have struck or any doubt? You have applied Cauchy's residue theorem? Did you get how many zeros are there? Singularity. What is the singularity here? Pi by 2 minus pi by 2. Why 10 pi by 2 will be singularity? Yeah, 10 pi by 2 is 10 0 0. Right. But pi by 2, what is this pi by 2? Yeah, pi by 2 it has singularity. Cos pi by 2 becomes 0, right? Minus pi by 2 is also inside this contour or not? Minus pi by 2, I think it's 1, 1, it is not. Minus pi by 2 is not here. It's only pi by 2. Okay, I will check that is there any easier way to solve this or not. Yeah, I think it might be useful that number of zeros by a number of poles argument principle might be useful. I don't know. Yeah, it is also connected to the Cauchy's theorem what we have done today. From there, you can also count the number of zeros and number of poles using argument principle. Okay, so it's already 7. So let's stop for today. We'll meet in the next class. Okay, I will see that is there any easier solution to how to solve this. I will remember this question. Let me stop presenting.